In 1977, NASA is given an enormous challenge: build a space telescope with the potential to unlock the secrets of our universe.
It's an engineering wonder. It really is an engineering miracle.
The project pushes engineers, scientists, and astronauts into uncharted territory.
Liftoff of the Space Shuttle Discovery with the Hubble Space Telescope.
We put our careers and our lives in that shuttle bay.
From construction to release.
Solar panels wouldn't go out. They were stuck.
I need answers now.
From ridicule.
I thought that there was no conceivable way that they could fix this.
To redemption.
Man, that was a neat moment.
It's a classic story of human ingenuity and human perseverance.
This is the story of the unsung heroes who built the Hubble Space Telescope.
Discovery, Hubble is open for business.
December the 7th, 1993. In the lethal environment of space, astronauts risk their lives trying to save the $1.5 billion Hubble telescope.
We had to do it. The future of Hubble was at stake, perhaps even the future of our agency.
The servicing mission was a technical challenge like none anybody had ever seen.
Delicate new hardware must be installed. Without it, the telescope's performance is critically impaired.
You've got this huge spacesuit on with big, thick gloves. How in the world are you going to do very fine electronic work?
You check your mechanisms, cock store.
People considered that to be the most critical maneuver. If I tap that thing, it's over.
Okay, are you ready for me to let go? Yes, I have it.
For over 2 decades, the Hubble Space Telescope has provided humanity with unparalleled views of the universe.
Hubble isn't just a satellite. It's about humanity's quest for knowledge.
Before it, images of this clarity simply didn't exist.
Hubble shows us the beauty of the universe. We all can look up at the sky at night and wonder what's going on out there. Where did we come from? Who are we? Is there anyone else out there? And Hubble helps us to come up with the answers and shows us the absolute beauty of what's out there.
The great fun of science is that it answers questions and that it creates questions, and Hubble's done both.
Named after American cosmologist Edwin Hubble, this school bus-sized observatory circles our planet at over 25,000 kilometers per hour, capturing light 6 billion times fainter than the human eye can see.
Your eye can see more or less a flashlight, a 2-cell flashlight, maybe a couple miles. Hubble could see that flashlight on the moon, 240,000 miles away.
Just keeping the proposed telescope steady enough to take photographs in space demands unprecedented engineering.
Hubble had to be stable with an angular precision of 7/1000ths of an arcsecond. This would be analogous to putting a laser on top of the Washington Monument in Washington, D.C., and illuminating an object the size of an ordinary 10-millimeter pearl at a distance of New York City, and never going off that diameter of that pearl for 24 hours at a time. This is hard, folks.
The incredible journey to build this revolutionary machine begins over 70 years ago. September 1946. American astrophysicist Lyman Spitzer writes a short paper that changes the course of history. He's frustrated with trying to observe space from the Earth's surface because our atmosphere blurs the view of the heavens.
You know that Twinkle, Twinkle, Little Star? Well, everybody loves that song. Astronomers hate it because they want to get rid of that twinkle.
Earth's atmosphere also filters out wavelengths of light such as ultraviolet that are critical for unraveling the evolution of our cosmos. Inspired by advances in rocket technology, Spitzer makes a revolutionary proposal: an orbiting observatory above our atmosphere.
The idea of putting a telescope in space, I mean, give me a break. We didn't even have satellites when Dr. Spitzer wrote that paper.
Spitzer devotes the next 3 decades to promoting cutting-edge research which will make his dream possible.
What Lyman Spitzer did is move the space telescope idea from pure science fiction to you might actually be able to do this.
In 1977, his efforts are finally rewarded when Congress approves funding for a space telescope. NASA must now deliver Spitzer's dream. But building this telescope is an immense technical challenge. Chief Engineer Jean Olivier shoulders much of the burden.
Hubble was an extremely ambitious program. The further we got into it, the more ambitious we realized it really was.
Before construction of the telescope can even begin, NASA must decide how to launch it into orbit. As it happens, the agency's crown jewel, the Space Shuttle, is in the final stages of testing.
As NASA put all of its dimes into the Space Shuttle, many scientific missions had to be redefined in terms of being carried by the shuttle.
Fitting into the shuttle's cargo bay, the telescope will be latched to a tilting mechanism and
putting Hubble into orbit with a reusable vehicle offers engineers a fantastic new opportunity.
The Space Shuttle was going to be there to service the Hubble and upgrade its instruments every 3 years or so.
To ensure Hubble can be improved over time, engineers design it to be modular. Each of its 5 scientific instruments, tasked with unlocking the mysteries of the universe, must be packaged in its own easy-to-replace box.
And so everything had to be done such that it can be removed, but removed by spacewalking astronauts.
But while using the shuttle extends Hubble's shelf life, it has one major drawback.
Basically, Hubble was built as large as it could be built to fit in the shuttle bay. I'm sure many of the engineers wish they had more room, as it turned out.
Hubble needs to be smaller and lighter than Earth-based telescopes, but also have more advanced scientific capabilities. And no instrument is more important to the tax-paying public, whose dollars fund the project, than the one that will provide the pictures.
If you would ask, what's the one thing that you have to have? The answer is you had to have a camera. But at the time, nobody had built a camera that had to be this good.
Unlike most telescopes on Earth at the time, it's not practical for Hubble's camera to use photographic film.
We had to have a camera that would work very remotely and send a signal back.
Restricted by size, the camera must be lightweight, robust, and sensitive to a wide spectrum of light. The battle comes down to 2 very different devices.
You had a choice that had been tested, the television-type camera tube. But then you had something new, something untested, but really promising, and that is solid-state silicon technologies that we call today charged-coupled devices.
These nifty electronic eyes convert light into electricity, building up a picture made of tiny individual squares called pixels. Smaller and more sensitive to light, the charge-coupled device, or CCD, appears to be the better bet. But there are serious drawbacks. They're untested, can't detect UV light, and they have a field of view much smaller than the television-type tubes.
It was pushing the state of the art a little bit too far, a lot of people thought.
With no clear winner, NASA puts out a request for proposals. Bob Odell is a prominent member of the selection committee.
I cannot say I made the selection, but I wouldn't have been in the room without having a strong opinion and expressing it.
At the California Institute of Technology, the challenge attracts the attention of two maverick professors, Jim Westfall and Jim Gunn.
Jim Westfall was wonderfully hands-on. He was absolutely a Thomas Edison type person. Jim Gunn was the scientist, well acknowledged to be one of the smartest guys in our field.
Since 1975, they've been experimenting with ground-based telescopes fitted with CCDs.
They were clearly the magic bullet, so we had to do this.
Autumn 1976. James Westfall agrees to lead the project and recruits an elite Caltech team to help engineer the world's most sophisticated camera. They begin fresh experiments with the technology they hope will form the core of the camera: charge-coupled devices.
You have a thing that's very, very close to this in your smartphone. The problem was that at the time this technology was very new, and though it was incredibly promising, it was also very risky.
Convincing NASA that CCDs are the technology to go for means overcoming some critical engineering challenges. First up, field of view. In the mid-1970s, CCDs are relatively small. This limits the size of image they can produce. But scientists demand that Hubble's camera has a wide field of view to record larger portions of the cosmos. To compete with television-style cameras, Westfall must increase the CCD's field of view by at least a factor of 4. As it happens, Bob Odell has a radical solution that he chooses to share with Westfall. Instead of building a single, larger CCD, he suggests using 4 smaller ones. As light from the telescope enters the camera, a specially designed pyramid-shaped mirror splits the beam and redirects it onto 4 separate CCDs.
So the final image is a mosaic of the 4 components.
Now just one daunting engineering roadblock stands in Westfall's way: capturing ultraviolet light.
People are very interested in what stars are made out of. They're very interested in what the gas in the galaxy is made out of. To understand that, you really need to look into the ultraviolet.
The trouble is, CCDs can't see in the ultraviolet spectrum because the silicon they're housed in absorbs it. Westfall must overcome this crucial problem.
Problems were something that Jim solved. So naturally, he was the guy who was going to do this.
For inspiration, Westfall turns to nature. He studies chemical reactions that occur in living organisms which create light. Through his research, Westfall unearths some potentially game-changing chemicals that can convert UV light into visible light through a process called fluorescence. To test if fluorescence can be recorded by CCDs, Westfall carries out top-secret experiments with 2 different chemicals. Each is given a code name to ward off competition.
They'd talk about it as bug juice or mouse milk, this kind of magical stuff that you put on the surface of the CCD.
Westfall coats the CCDs in either bug juice, the chemical lumogen, or mouse milk, the chemical coronine, by evaporating them in a vacuum.
Nobody had done that kind of thing before with these devices.
Next, the detectors are inserted into a camera, exposed to a UV light pattern, and a picture is taken. If the tests fail, Westfall and Gunn's dream to build the Hubble camera is over. The results with coronine are a breakthrough. The 2 main barriers to using CCD technology have now been overcome. Westfall's team have increased the detector's field of view and discovered how to record ultraviolet light.
We were able to convince NASA that this was a technology that worked, but mouse milk won over bug juice in the end. So.
NASA greenlights construction of Westphal's Wide Field Planetary Camera, known as WFPIC, with its core technology of CCD detectors. For the public, the camera will define Hubble's success.
We had to do great science, but also get that science to the public. So pictures were critical. And what instrument produced the neatest pictures? The Wide Field Planetary Camera.
NASA's chief scientist, Ed Weiler, pushes for the construction of a duplicate camera to keep in reserve.
Having an insurance policy that would only cost maybe $50 million was worth it.
After some cajoling, the NASA hierarchy approves the idea, and the following year, work starts on a replica camera, WFPIC 2. Crucial to the success of all Hubble's instruments is the design of the telescope itself. Telescopes capture light using lenses and mirrors. The bigger they are, the more light they can gather, and the more detail they can see. The further the light travels inside the telescope before it's focused, the greater the magnification. But because Hubble must squeeze into the bay of the space shuttle, it can't be as big as engineers would like. To extend Hubble's view into the universe, they boost its magnifying powers using a 300-year-old optical trick, hyperbolic curved mirrors. Reflecting light back and forth inside the telescope increases the distance it travels, making the instrument more powerful. It's the perfect solution to engineering a lightweight, high-performance telescope. But the success of this design hangs on the quality of the telescope's light-gathering primary mirror.
It's the brain or the heart of the telescope. That's where it all starts.
NASA contracts the Perkin-Elmer Company to undertake much of the complex technical work. This includes engineering the mirror.
The most challenging thing first was to build a mirror precisely enough to meet the resolution needs.
It had to be accurate over that 2.4 meter surface to a millionth of an inch.
If you were to take the diameter of Hubble and blow it up to the size of the Earth, then any deviation of more than about 6 inches would be unacceptable.
To achieve this level of precision, Hubble's primary mirror is carved from a 1-ton block of glass and meticulously polished with a spinning abrasive pad controlled by computers. After polishing sessions lasting up to 70 hours, the mirror's shape is analyzed in this chamber.
The task of the optician to make the Hubble mirror is first to create a device that allows him to measure the surface.
But creating equipment that can measure accurately enough is a challenge in itself.
With Hubble, we wanted to make a perfect mirror. And so the Perkin-Elmer, really smart guys, conceived of a thing called a reflective null corrector.
A null corrector is a precision optical test device. By shining a beam of light through this carefully calibrated instrument, engineers can create a light wave pattern in the exact shape of the desired mirror. This light is then reflected back by the mirror and the interference pattern recorded. Straight strips mean the mirror's curvature is perfect. A distorted pattern indicates it's the wrong shape. By studying these images, optical engineers know where to continue polishing the mirror to create the perfect curvature.
The null correction test is accepted as one of the most precise methods of testing.
But it's a painstakingly slow process that puts Perkin-Elmer badly behind schedule.
I think originally it was supposed to take 9 months and probably took twice that.
As preparations for launch begin, Perkin-Elmer deliver the mirror to NASA. What they don't realize is that a tiny flaw in the test equipment has gone unnoticed.
It was an oversight, and it had enormous ramifications in the life of the Hubble Space Telescope.
3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
January 1986, just months before Hubble is due to launch.
Challenger, go at throttle up. Challenger, go at throttle up. God, no.
The Challenger disaster plunges the Space Shuttle program into turmoil.
Obviously a major malfunction. Okay, everybody, stay off the telephones. Make sure you maintain all your data. Start pulling it together.
As America comes to terms with the tragedy, NASA grounds the shuttle fleet, and Hubble's launch is postponed indefinitely. For 4 years, it sits in hibernation.
Liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
Finally, on April the 24th, 1990, after 13 years of blood, sweat, and tears, Hubble is ready to leave Earth.
By the time we launched, about 10,000 people had spent some part of their lives working on Hubble.
Roger roll, Discovery.
And you realize that sitting up there on the very top of that pillar of fire is this thing that you have attached your life to. This thing that is carrying the hopes of a whole science.
Discovery's velocity now 2,300 feet per second.
It kind of takes your breath away.
Discovery soars to over 600 kilometers, higher than any shuttle has flown before, to place Hubble above the Earth's atmosphere. Now it is time to set the telescope free.
Discovery or go to transfer Hubble to internal power on time.
Roger that, understand. Go for transfer to internal power on time.
Story Musgrave is capsule communicator at Mission Control.
I knew the importance of that mission. I knew what Hubble meant to people.
To generate power, Hubble relies on 2 solar arrays, absorbing energy from the sun. But to unfurl the arrays, there is a critical stage where Hubble must run on internal batteries. NASA must deploy the solar panels before the batteries run down.
Once you've taken the power off of Hubble, it's going to die. So we're time constrained.
The first panel unrolls perfectly. Now, time for the second.
Houston, Discovery, it looks like motion stopped with just about 1 panel showing.
They're supposed to motor out, and it wouldn't go out.
It's like you're watching the birth of your baby and it's stuck. It's a big deal.
Okay, with the panels that you got out there right now, it's not satisfactory to stay overnight.
Years of work and billions of dollars are at stake. Engineers must find a way to release the stuck panel before time runs out.
I need answers now.
The problem is quickly diagnosed.
Discovery, go ahead.
We think there may be some problem with the tension monitoring software.
A sensor is saying tension in the panel is too high. One solution is to override it. But this could snap the solar array's stem booms, rendering them useless. It's risky, and engineers are split.
We need to get on with it.
Under pressure from flight control, Jean Olivier is in the hot seat.
Finally, it became clear we were at a deadlock, so I just had to say, no, we're going to do it. We're going to override it.
We are disabling the tension check.
Okay, Houston, we see motion.
It's fully deployed.
You let the breath go out, you let the air. Okay, we got through that one.
Now receiving the full power of the sun, Hubble can finally fulfill its primary purpose: to capture the universe in unprecedented detail.
In Discovery, Hubble is open for business.
We got our telescope. We got our telescope.
That's it.
Good luck, Bill.
May the 20th, 1990. Scientists and engineers eagerly await the telescope's first image.
The first image comes down, and it doesn't look at all like what we expected it to. Not these sharp little images, but instead were kind of these big blobs that frankly didn't look any better than the ground-based image.
Something has gone drastically wrong with the $1.5 billion space telescope. But what? June 1990. Over the next month, every effort is made to understand what's causing Hubble's blurred vision.
It was a puzzle, a very dark puzzle.
Part of the WIFPIC camera team, John Holtzman and Sandy Faber analyzed 6 further images taken by the telescope. They hint at a catastrophic problem: spherical aberration. Spherical aberration is caused when the primary mirror is built the wrong shape so that it fails to focus light into a single point. Instead, light is smeared out and the object appears blurred. It's such an unlikely mistake that many engineers and scientists can't believe it's true.
I don't think any of them would have predicted that something as basic as the curve on the mirror would be wrong.
We're sure that spherical aberration isn't going to be a problem. You know, nobody's going to screw it up that badly.
But Holtzman and Faber have compelling evidence that supports the theory. Holtzman shows the NASA hierarchy a comparison of 6 photographs taken by the telescope with a series of 6 computer-simulated images with spherical aberration built in.
And the match was nearly perfect, and I think that kind of proved to everyone that that was the problem that we had.
The most accurate mirror ever made is flawed.
It was made very accurately, very beautifully to the wrong prescription.
In July 1990, an inquiry into the cause of Hubble's faulty mirror reveals a mistake with the test equipment, the null corrector.
It wasn't quite aligned correctly, and that built into the whole operation an aberration.
Misspacing the null corrector by only 1.3 millimeters, the outer edge of the mirror was polished incorrectly by 1/50th the diameter of a human hair.
We very precisely did the wrong thing.
The management error was that there was not enough checks and balances.
Now we'll open the floor for questions.
Of Hubble's 5 scientific instruments, the wide-field planetary camera is the worst affected. It's a major blow for everyone involved with the telescope.
It would be dishonest of me to say this, the mood of the scientist is very happy right now. We're all frustrated, obviously.
If you ever want a picture of a person just in anguish, go and find a picture of Ed Weiler at the end of that press conference.
We feel right now that there's probably no real science that we can do with the wide field camera at this time. And I'll stop there.
It was very depressing, because a lot of us had put our lives into this our entire careers. Clearly, Hubble's future was in doubt. Perhaps the space shuttle's future was in doubt. Perhaps NASA's future was in doubt.
Some of the founding fathers are so disillusioned, they leave the project altogether.
About this time, I didn't have enough faith in NASA. I thought that there was no conceivable way that they could fix this.
The press have a field day at NASA's expense.
God, they were vicious. One that I remember, Jay Leno, he just hit it again and again and again. And one of the jokes that I remember, it was around Thanksgiving, and he said, what sound does a space turkey make? Hubble, Hubble, Hubble.
As public support for Hubble dwindles, it appears the dream for this space telescope is over. But Charlie Pellerin, the man in charge of the Hubble program, refuses to give up hope.
This was a horrible, deep pain, and only one way to get rid of it, and that's to find a way to fix the telescope. There was no other way.
The burning question is how to correct the flaw. Pellerin risks his career by secretly bankrolling a mission to find an engineering solution.
So I brought in my budget analyst, and I said, I want to find $60 million. And by the way, you can't tell anybody we're doing this.
The fact Hubble can be serviced by astronauts offers a glimmer of hope.
If there were no way to service the Hubble, Hubble would have rapidly become, in 1990, a very expensive piece of floating space garbage.
It's only now that Ed Weiler's decision to build a backup camera becomes a masterstroke.
And thank goodness we had that clone ready to go, because it was a simple fix to change out 4 little nickel-sized mirrors.
These mirrors divert the light from the telescope to multiple electronic detectors within the camera.
It was like going to the optician and saying, well, your eyes aren't quite right. You need this corrective lens. We put that correction on those little mirrors.
It's an internal fix that can be done by engineers on Earth. When it's installed, the new modified backup camera will go some way to fixing Hubble's vision. But saving the 4 other instruments that scientists hope will unravel the mysteries of our universe proves much more challenging.
The other instruments didn't have clones being built of them. There were no second copies.
These instruments require an external fix that can only be done by astronauts in space. The goal is to place corrective mirrors deep inside Hubble, in front of the remaining instruments, to correct their vision. But squeezing them into a very restricted space proves a technical nightmare. Jim Crocker is part of a multinational team tasked with finding a solution.
There were literally hundreds of ideas, but all of these were either impractical because an astronaut couldn't do them in gloved hands, or because it was too dangerous, such as going down the barrel of the telescope where an astronaut might be trapped.
A mechanical fix is needed that won't put the astronauts at risk. But the team struggles to come up with a viable design. After a conference in Germany, Crocker returns to his hotel.
I went to take a shower, and when the maid was cleaning the room, she had folded the arm down and slid it all the way down to the bottom. So to take a shower, I had to slide it up and raise the arm. When I did that, I had this epiphany. The shower head got me into a different way of thinking. So it was the idea of raising something up above the other instruments and flipping it out to do the correction that we hadn't thought of before.
In this moment, a corrective optics device, CoStar, is born. It will be pre-packaged in an astronaut-friendly box with mirrors that deploy remotely. The only downside, one of the existing scientific instruments will have to be sacrificed to make room for it. Crocker's showerhead-inspired invention is now displayed here at the Smithsonian's National Air and Space Museum.
This is the elegant engineering solution to what was a daunting technical challenge. The little mirrors that you see were deformed precisely to counteract the flaw in the main mirror. And only once the entire box was inserted, with everything protected inside, did the column extend, and then as it extended, deployed these little stalks with the mirrors into the optical beam of the other instruments.
To repair Hubble, both WIFPIC 2 and CoStar must be installed by astronauts on a series of grueling spacewalks. This takes 3 years of meticulous planning.
Stop, up.
Story Musgrave, who's been working with Hubble for 15 years, is the first astronaut to be recruited. To prepare his body for the spacewalking ordeal ahead, Musgrave goes to extraordinary lengths, enlisting the help of Olympic athletes like figure skater Dorothy Hamill.
I brought athleticism into the spacewalking world. If you look at a spacewalk, it is the choreography, the dance of this body and the tools that's going to get to the finish line, and that's it. There's nothing else. That's it.
As expectations of rescuing Hubble grow, the mission becomes more than just repairing a telescope.
It wasn't just Space Telescope that was on the line. It wasn't even NASA that was on the line. It was the broader question of, do we still do big science? If the servicing mission had failed, that may well have been the end of trying to do things like this. And we knew it.
We just had to do it and do it right.
30, SOB ignition.
December the 2nd, 1993, Kennedy Space Center.
Roger roll, Endeavour.
Space Shuttle Endeavour thunders skywards on a mission to rescue Hubble.
We put our careers and our lives in that shuttle bay.
It's quite a sight.
As Endeavour approaches Hubble, the crew reaches out with the robotic arm to capture the telescope.
Houston, Endeavour has a firm handshake with Mr. Hubble's telescope.
We copy that, Cubby, and there are smiles galore down here.
With Hubble tethered, the astronauts embark on a series of perilous spacewalks.
People are willing to put that suit on and go out there and try and fix a science instrument is heroism at a level that almost unparalleled.
After 2 days of intricate repairs, Story Musgrave and Jeff Hoffman removed the original wide-field planetary camera in order to install the backup, WIFPIC 2.
Okay. You check your mechanisms cocked, Story? I just cocked them, yes. I pushed on them.
At the front of the unit is a delicate instrument that diverts light from the telescope into the camera, the pick-off mirror.
This was the most critical part of 40 hours of spacewalking. If I touch that mirror, it's over.
As the world watches, Musgrave and Hoffman slowly maneuver the WIFPIC 2 camera into position.
These astronauts have to take this thing and somehow manage to slide it into this bay.
Looks like it's in there. Yeah. Okay. Are you ready for me to let go? Yes, I have it.
The camera is installed without a hitch. Now for the corrective optics device.
Keep coming up, coming up, coming up.
Pre-packaged in a module the size of a telephone booth, the device is key to every other instrument on Hubble working perfectly.
The booth just went in, bang, put the power tool on, it's done.
The crew of Endeavour complete one of the most ambitious repair missions in the history of space exploration.
Through your superb efforts, you have really shown that NASA can do all that we promised to do and more.
Good job. That's great. Congratulations.
Thank you.
Joe.
But has Hubble's eye surgery been successful? 4 days after Endeavour's triumphant return to Earth, Hubble's new camera transmits its first image. It's the moment of truth for those who've dedicated their lives to the telescope.
And the image comes down, and here it is coming up on the display. And it was right. I mean, how do you describe that? How do you capture the emotions when you've been a part of something that was built up with such incredible high hopes? Man, that was a neat moment. God, that was a neat moment.
And then having that first picture come down and prove, and absolutely prove, that we had fixed the Hubble Space Telescope, that was a moment of redemption.
Get it!
I said, holy and I wasn't fired for it.
Over the next quarter of a century, Hubble observes more than 30,000 objects and beams back over 500,000 images. Its discoveries transform modern astronomy.
And you think about it and you're looking 10 billion years back, and you're seeing history in front of your eyes as the light comes. And it's an amazing thing.
Witnessing the birth and death of stars, confirming the existence of supermassive black holes and thousands of unknown galaxies, and measuring the age of the universe, Hubble's science and images transfix the world. Between 1993 and 2009, 4 further shuttle missions returned to upgrade Hubble. Aboard 2 of those is astronaut Mike Massimino.
Okay, man, you have a go.
There we go. I think it's the greatest scientific instrument ever built, not only because of the science it produces, but because of the engineering that went into it. What a beautiful view. It's an engineering wonder. It really is an engineering miracle.
But after a quarter of a century in orbit, and with no more servicing missions planned, Hubble's days are numbered.
And we wish Hubble the very best.
Now, there's a new kid on the block. Set for launch in 2018, the James Webb Space Telescope will extend our window into the universe.
We're going to see unprecedented views of the birth of stars and planets, the origins of life.
As with Hubble, engineers work tirelessly behind the scenes to ensure the mission's success.
The thing that keeps me up at night is the problem we didn't think of, so-called failure of imagination.
While the James Webb Telescope is the future, Hubble's engineering tribulations and eventual triumph ensure it a prominent place in history.
Hubble originally was sold as this instrument that was going to revolutionize our understanding of the universe, and it delivered on that promise, I think, more than anybody could have dreamed.
And all this has been possible because of the scientists and engineers who turned humanity's dream of a space telescope into reality.
In the dark days of the mirror flaw, if you had told me that I'd be sitting here after Hubble's 25th anniversary of successful observations, I would have said you're crazy. The commitment to find a way to fix it is one of the great things I've ever done in my life.
The lessons learned transcend engineering and science.
We tried something hard, it's important, and we screwed up. And it was such a screw up that the whole world laughed at us. But the important thing in that story is perseverance. We kept trying, and we eventually succeeded.
And that's a story that we humans love, and it's certainly one that I loved having been a part of.